Yeah. So I'd like to talk about designing of validation pipelines and about two common pitfalls and how to avoid them. Partly, this talk was inspired by the first lecture by Russell Pollock, because he told a lot about various ways to overestimate your results, and here I'd like to show you two ways to do the same thing, so to overestimate your accuracy of your machine learning pipeline. And as a side story, I also like to give you a brief introduction on two topics. So the first one is feature selection, and the second one is selection of hyperparameters. And I'll start with two simple data sets, artificially generated, and then we'll work with more complicated one, which looks like a typical neuroimaging data set, a lot of features and a relatively small number of observations. So it's just a brief overview because we don't have enough time to dive into details. There are three main groups of feature selection algorithms. So what's the main idea? We have a lot of features, and we think that not all these features are relevant, and we want to somehow select a subset of these features and then perform our machine learning, like building a classifier. So there are three main groups of these methods, and I'll show you a couple of examples for this and some examples for this. So let's start. It's a standard import of standard tools. Let's start with filters. So the idea is very simple. We can select one feature, then somehow estimate its importance or its kind of score, and then do this operation for all available features, and then select k features with the highest scores. So it's pretty simple, and there are a lot of ways to calculate this score, and I'll show you two popular examples, and you can read more using scikit-learn documentation. So let's start. So it's import of necessary stuff. Let's start with a simple example. We can generate a simple data set. So it's just a very simple two-dimensional artificial data set, and we can visualize it. It looks like this. So we have, it's a classification problem. So we want to separate blue points from green points, and we have two features. So it's clear that for this particular problem, the most important one is feature x0. So unfortunately, it's x0. So using only one feature, we can perfectly separate this data set using these two rules, and x1 can be used with some degree of precision, since it's a little bit shifted. You see, blue points are lower than green points, but it's clear that we should select x0. So let's try to apply these two methods, which will be were inputted from scikit-learn. So the first one is just simple. And also we're trying to build a linear model, and one-dimensional linear model, and estimate quality of prediction. And so to perform the experiments, we need this select k-best method. It's a standard transformer from scikit-learn. It allows to estimate scores, specified scores. In that case, it's f-class if. for each variable and then select a specified number of variables. So here we would like to, for our two features, we would like to estimate F classification score, and then we can read about it. So it's to open this help, you should press Shift plus Tab. You can press it multiple times to see more detailed help. And so this one is a simple criteria to estimate importance of scores, importance of features, and it's a very simple transformer. So it takes all our data set, performs this estimation of feature importance, and then select a specified number of features and return these features to us. So we can check how it works. So we can print shape of our original data. Then we can transform our data. And print shape of then this reduced data set. And you see we select one column, and this scores allows us to compare its values for this F-class if scores for these two features. And we see that this classical approach select the second feature, so x1 and not x0, because importance for this score is significantly higher than this one. And the reason is very simple. This score tries to build a linear decision boundary, and it's clear that we cannot build a simple boundary for this linear boundary for this data set. So it means that this simple criteria can be useful for simple cases, but for these cases with perfect separation between two classes, it selects the wrong component. Please feel free to stop me if something is unclear.
Can you go to the other slide?
To show this criteria, help for this. You mean this? Yeah. Mm-hmm.
You have used selector to select how many features?
To select one feature as I requested. Out of two, yes. It's a very simple example.
Okay.
Yeah.
And calculated score for only one feature?
No, internally we this method calculates scores for all features, and we can print these scores, and then select K best features, so K features with the largest scores. Now K is equal to 1, so we would like to select only one feature out of 2. So it calculates 2 scores and then select one feature as we requested with the highest score. So it's the second feature. Okay, so what we can do with this wrong selection, we can use another type of criteria, so another way to estimate scores. It's mutual information. It's widely used in neuroimaging software, for example, when we perform co-registration as a measure of, again, concordance between two images. And also we can use it to estimate these scores, so to estimate mutual information between our target variable and between our target variable and each feature. So it's just another way to estimate scores, and the algorithm remains the same. So we estimate scores and then select specified number of features with the highest score. So we can try apply mutual information to this artificial data set, and it's a better way to estimate dependencies between two variables. It can be considered as kind of piecewise estimation. So now we see that for this criteria we have a reasonable result. So for first feature we have higher score, and for the second feature we have pretty low score. So in that case our select best transformer selected the first feature. Okay. Well, so let's consider another example. It's another data set, and it's a three-dimensional data set, and you see that we have two variables, so it's x0, x1, and x2. And these two variables can be used to perfectly separate the data. So we can build such kind of a plane to separate our classes, and the third feature isn't as relevant. So ideally we would like to select these two features, but the problem is that we have to consider these two features as a combination. So in this case our univariate methods, which tries to estimate scores for a single variable, will probably fail because they cannot catch this multi-feature interaction. So we can try. We can estimate. Again, we can okay, we can replace 1 by 2. It doesn't matter. So what we see here, we estimated scores for two different by two different methods for this task, and as we see, there is no clear difference between these three features, and both methods prefer to select the last one, the less informative one. So it's just an example of our incorrect results for this methods, because it's this class of methods is too simple, so it cannot catch such multidimensional dependency. So let's go to another class of methods which can be used for such problems. It's so-called wrappers. So the idea is again pretty simple. We can start with a whole set of features and then drop irrelevant features one by one. So we build a model. For example, how can we do it? We can build a model using all features and then estimate which feature isn't very important, is even the less important feature for this particular model. Then we drop it and re-estimate our model using the reduced set of features, and then we can repeat this procedure required number of time, and finally obtain some some set of features. Again, we can use different strategies, and probably the most frequently useful and the well-known method is recursive feature elimination. You could read more about this method here. So let's apply this method to our artificial data set, three-dimensional data set. So we need some model with which allows us to estimate importance of each feature, and we need this transformer to select requested number of features. So we can fit it and then select a ranking of the features. Again, it's a very simple example. We asked to select 2 features. So this ranking means that the algorithm drops this feature, so it's rank the lowest one, and keep these 2 features. So it means that it selects, since it can catch multivariate dependencies, it selects to the right features. Okay, so also there is another, the third type of yeah.
Question for the wrappers. So there I have to first finalize the model which I'm gonna use, and then a feature selection method which is RFE, right? Many times what happens is we have a feature matrix and I don't know which algorithm I'm gonna use. So in that scenario, that might not be a good idea to use that, right?
Yeah, maybe. Yeah, maybe yes. Yeah, here you have to use some kind of method inside, and it's usually a linear method. It can be a linear SVC, or it can be logistic regression or linear regression. In principle, you can build more complicated pipelines. So the first step will be feature selection using these methods, and then you can apply some nonlinear method to the reduced number of features. In principle, you can do.
Isn't that like there might be a case where I have, let's say, 50 features. Out of 50 features, one of the feature is important for SVC, and important, like let's say feature number 3 is important for SVC when I give it to this algorithm.
Yeah.
And feature number 4 is important for SVM. Okay. In that case, like there is too much of variation. Like I'm not able to know whether I should do feature selection first or select the model first. So
yeah, ideally, you would like to observe consistent importance of features between various methods. Ideally. So SVC is just support vector machines for classification. So SVM for classification in terms of scikit-learn. SVR, it's support vector machine for regression. So it's just a name in scikit-learn. So it's both SVM. Yeah. So ideally, you would like to observe that you can change methods and still find the same important variable. So approximately the same. Yeah, let's go further. So the next class of methods is kind of embedded methods, and a good example is a linear model with L1 regularization. It's kind of lasso regularization. I really like this plot. It's a little bit complex, so it just shows that you would like to optimize some functional and in a certain area. So it's kind of a constraint, and you would like to find where your level linears touch the boundary, and it's just a comparison of 2 types of L1 and L2 regularization. The core difference is that L1 regularization allows you to obtain a sparse solution. So let me show. The sparse means that some coefficients are equal to 0. So this means that you have some coefficients equal to 0, that these variables aren't important. Yeah.
What if two variables are correlated?
Yeah, sure, it's a problem. Yeah, it's a problem with L1 methods if you have correlated variables.
And the previous one, the feature discarding, if you have two variables that are equally predictive, if they're exactly the same, does it then check one of them and just randomly pick one, or does it keep both?
So if they are important, the method drops other features before, and then it just selects randomly. So if we have, for example, two important variables and a number of unimportant, and asked for only one important variables at the end.
What if there are two that are perfectly correlated?
It will be just kind of a random selection. Yeah, and also we have similar problems with L1 penalty. And I'll show it here. So in that case, in this artificial example, we have perfectly correlated variables. Variables x0 and x1, they are pretty good correlated. So we can start with this logistic regression, and we can specify that we want L1 penalty, which can give us sparsity, and then we have to use this parameter to select this regularization parameter. So it's area of this constraint. Higher values will lead to smaller regularization. So we want to impose more strict constraints. So perfect regularization. All coefficients are 0. So here we have, it's an example of how these embedded methods can work with if we have perfectly correlated variables. So you see it drops important variable. As you remember, we would like to have these two variables. But in that case, it drops this variable, and we still have this not very important variable. So it's a problem when you have correlated features. These methods can lead to wrong results. And just an example. So we can redefine our data sets to make the last component absolutely relevant. So just kind of random noise. Just a modification of this data set. So you see there is no large. These two clouds are perfectly overlapped now, and we can use this data set again with this method to estimate. As you see, it's again drop one of two important variables, but if we impose less strict constraints, we'll find the right features. So it's just a brief overview of 3 types of methods. They all have some disadvantages, so you should use these methods with care. And I'd like to show you a simple example. Unfortunately, we don't have enough time, so I do all necessary work. So it's another kind of data set. It's kind of an anonymized data set, so it's all features have 0 mean and deviation equal to 1. And now it's a pretty large number of features. So you see we have 121 samples and approximately 5,000 of features. So it's it can be very typical for neuroimaging. So imagine that it's your number of subject and this, say, number of voxels. And you would like to, so the idea, and you have, now it's a classification problem, so you have two, it's a binary classification problem. You have two type of labels. And so the idea is the number of features is too high. Let's somehow select a subset of these features and then estimate accuracy of our classification. So we can start. Yeah, it's just an example of how it looks like. So it's just a lot of features, anonymized features, and just a big table. Okay, so for example, we can use this select key best features, and say we just decided that we need only 50 features, so just more or less a random number. So we can fit our transformer, and as usual at scikit-learn, you can do two operations at the same time. So fit and transform your data. So now we have, you see, shape of new data is as we requested. We have now 50 features. Now we can try to estimate accuracy. So here I use logistic regression and automatic method from scikit-learn, which internally performs cross-validation. So it splits our data set into 5 parts, then train 5 different models, and estimate accuracy for each split, so for each part of data, and then return these scores. And here we can check its number of splits. So we can check individual scores. So you see it's these numbers. So it's accuracy of classification, and 1 means perfect classification. So it seems that we have a very good result for this data set, and but probably it's too good. And it's really the case because I made a mistake. And how can we it just for comparison we can use so you see here we have reduced x reduced, and here we have original data. So just to compare, we can use the original data set, and you see accuracy is pretty low. Actually, you can use you can select 0 all the time, and your accuracy will be slightly less than 0.6. So it's kind of magic. So what's wrong with this? There is a very simple way to validate your approach, your processing pipeline. You can randomly shuffle your labels. So if you randomly shuffle your labels, you can expect that your results will be just as a random classification. So these two comments allow us to randomly shuffle our new Y random variable. So now I repeat the analysis, just replace Y by Y random, and we see again the same classification accuracy. So what's the problem? And it's a typical mistake. The problem is that I use all my data set here to find important features, and only then I perform cross-validation. So my validation sets aren't independent because they were used for this step. So it's the problem. So it's not evaluation on the independent test set, it's evaluation on set which already be used for some kind of processing. So how can we avoid this? We should use pipelines, and it's not as complicated as NumPy pipeline. It's very simple pipeline. So all you have to do is use this make pipeline function from scikit-learn and chain these two steps of analysis into a single pipeline. So select k-best and then logistic regression. And now we can estimate scores for this aggregate random variable and for this variable. And you see actual, using this pipeline, so you see actual errors on the level of random error. And the way I generated this data set, it was pure random generation. So it's the first pitfall, which I observed multiple number of times, even in good papers. So please chain your steps into pipeline. Yeah.
So are you doing a cross-validation on both steps? Is that what's happening?
Here, yeah, here cross-validation. So here we built kind of a merged pipeline. So for cross-validation, it's just a single object with fit and transform, fit and predict methods internally. It's for when I use fit, I can launch pipe.fit. It's use fit method here. Then apply transform to my data and feed this new data here. So it's impossible to somehow split these two steps if we use these steps inside the pipeline.
So it's handling, it's doing kind of a double cross-validation, is that right? Where it's not selecting features based on part of data that's been untouched and then doing So internally we split our data into 5 approximately equal parts. So we have approximately 25 points as a validation set and approximately 95 points as a training set. So we feed this 95 points here, select features which are relevant for these 95 points. Then we will obtain kind of matrix of 95 observations and 50 features, and then feed this new matrix to logistic regression, and then perform the same analysis for validation set. So just select these selected 50 features for our validation set and feed it to logistic regression to obtain predictions. So on validation set we use only transform or only predict method. So we don't do fit on our validation set. So it's the idea. Use our test or validation set for validation only, not for training.
And feature selection, you are using a part of training.
It's automatically it's embedded into cross-val score function. It split our data into several chunks, and that feed one chunk, actually 4 chunks, into fit method, and the remain chunk to predict methods. So it's probably it can be written as kind of 5-line cycle. It's just a shortened version of cross-validation. Okay, cool. So it's another example. Now I'd like to talk about selection of features, about selection of hyperparameters. All our datasets all our methods have some kind of parameters. So it's a very simple data set. It's one-dimensional data set. It's a true function. It's a true function plus kind of noise. So red points are our training data. And I'd like to use the following pipeline. So it's polynomial features. I use my one original feature to generate here to generate 20 features. So x in power of 1, x in power of 2, and etc. x in power of 20. So it's kind of polynomial. So I'd like to fit polynomial function to my data. And as fitting model, I use ridge regression. It's a linear model with L2 penalty. We can use any linear method here. So, okay, we can fit our data pretty good. We can also estimate error, so not just visually inspect quality of prediction, but also estimate an error. Here it's root mean squared error, a typical choice for regression problems. So what's about parameter? It's a very famous concept, and it's a good introduction into this concept, that our error on test set can be considered as the sum of two different parts. It's kind of variance and bias, squared bias. But what's important for us is that we want to modify complexity of our model to find this black arrow. It's an error on test set. So we'd like to modify complexity of our model to find optimal error on a training set. So again, unfortunately, I don't have enough time to go deeper. I recommend this tutorial for this topic, and we can use this parameter, regularization parameter here to control complexity of our model. So very low number here means that we use two complex models. So you see it's a lot of oscillations, and it fits training set almost perfectly. So our curve goes through almost all points. So it's too complex model. Or we can use very large value of regularization parameter. And it will be very simple model. In that case, too simple. It's just a straight line. So we constrain our coefficients very hard. Or we can use something in the middle, like 0.1, and we'll observe pretty reasonable figure. So what's the case? How can we select these parameters? Actually, we can use so-called grid search. We can specify that we have some kind of parameters, and we would like to check different values of these parameters. These lines mean that we generate 21 equally spaced number from -5 to 5, and then use it as a power of 10. So 10 in the power of -5, 10 in the power of -4.5, etc. So it's kind of a grid of parameters. So we would like to check all these parameters and select which value of parameter is the most appropriate for our problem. And we can use this grid search method if we have pipeline, and it's the case, we have pipeline with 2 steps. We can specify name of parameters, so it's name of step here at ridge, double underscore, and then name of parameters. So we can simply add here another set of values, for example, for number of polynomial features. But here I just like to use only ridge alpha to select only regularization parameter for ridge regression. Sorry. And where is it? Yes, sorry. So, yeah, I skipped this cell. Okay, so as we can see, this automatic search finds a reasonably good parameter of organization parameter. And what can we do if we have a lot of parameters? For example, we can use gradient boosting tree classifier. Unfortunately, we don't have enough time to wait for execution. It takes maybe 7 minutes, maybe 10 minutes. So I have to stop it, and I'll describe the main idea. So actually here we have like three set of parameters, and this grid search, as suggested by its name, use all possible combinations of parameters and launch a lot of models inside to check all these parameters. So here we have 80 combinations of parameters. So internally it launches 80 cross-validations, estimates 80 errors, and then select a combination of parameter with the optimal error. So with the, in that case, with the smallest, with the it's classifier. Okay, with the highest classification accuracy. You see, it's again dataset free with random labels, and the idea is that if you launch this code, you will observe non-random error. And the reason is that you do kind of multiple comparisons. So you launch a lot of different models, and error of each model, it's a realization of a random variable. And you can select just, you can simply overestimate your error just by picking a score which is far away from mean score for this number of parameters. So let me show a very simple example which illustrates my idea. So let's return to this data set. So we can observe that our model is a kind of random model. We can regenerate samples with new random noise, so it's kind of new realization of our sample, and we can see that our model is also changing, and our error is also changing. You see, so it's for each, and the set of parameter is fixed. So I don't modify my model. I just modify my training sample, and I observe different results, and it's natural. So what does it mean? It means that for each set of parameters, actually I have a kind of distribution of errors, not a single error. It's a distribution of errors, and how grid search selects the optimal parameters. It just takes a single realization from this distribution, so it can be here and it's okay, or it can be here, or it can be here, and this means that we can overestimate actual accuracy of our model just because we don't have this distribution. We don't see it. We see only one particular number. And ideally, we can suppose, okay, so what if deviation of this distribution is pretty small? So what if we have very narrow distributions, and in that case, it's okay. So we can be sure that actual error is pretty close to the observed error. And here just a simple example for this data set. So this is regularization equal to it's almost zero regularization. So here we have very variable model. It's well, we can see, I guess. So we can 1 minus. It looks like this. So 2 variable, and you see distribution of errors from 0 to 300. So it's pretty unstable model. So then we can select a little bit more robust model. So it looks like this. So you see still some oscillations here, but not as still quite bad. Well, for this model we have this distribution of errors, so from 0 to approximately 3, and this is almost optimal model with 0.1, and so from 0.1 to 0.25, and this model is just a constant model. You see very narrow distribution from 0.32 to 0.36, and so my key point is that during grid search CV you won't observe these distributions. You will observe only a single realization. And so it's okay, it's a limitation. We cannot calculate 100 of times cross-validation for each set of parameters. It's computationally too expensive. But the key idea is that you shouldn't use your score from grid search CV as a final score of your model. You have to validate your optimal set of parameters. So you can use grid search to go for a lot of various combinations, then select one, and then do this procedure, or at least repeat it at least 10 times to validate this optimal set of parameters. Because for this case we have smaller means better, so it's a regression problem. And it's usually you will observe that optimal score selected by grid search CV will be somewhere here, so it will be over optimistic. So grid search is okay, but you should validate the selected combination of parameters using an independent test set or using several repeats of your cross-validation procedure. And so the second pitfall is that people usually report these only values from grid search CV, just this value which were found as an optimal value, and usually it's too optimistic. So these are some conclusions. So an ideal situation, if you have an independent test set, so you do all your machine learning in any way you want, and then test your final model on independent test set. But it's clear that in neuroimaging we have too small data sets, so we have to do some kind of cross-validation to use all the data in our pipelines. So if you do multi-step analysis, selection of features is just an example. It can be different steps. You should always merge these steps into a single pipeline and estimate accuracy of this pipeline as a whole undividable thing. Also, you can use this random shuffle to check that that everything is all right. And again, you can use a grid search CV to select your optimal number of parameters, but you should recheck actual quality of the selected combination of parameters. Oh, that's all. Yeah.
Thanks, Mikhail. So what would you recommend when reporting the like reporting the whole distribution with this, or just
Yeah.
the main?
At least you should show mean value and standard deviation, or you can use there are beautiful plots in Seaborn called Wheeling plots. So this allows you to visualize your distributions in a pretty cool way. Yeah, it's kind of this thing rotated. Yeah. So at least standard deviation, and it's better if you can show actual distribution. Yeah.
You do an external cross-validation. Your first bullet point there. If you have an entire pipeline set up, do you want to run your pipeline in any cross-validation you're going to do internally and then have a completely untouched data set? Or is it okay to kind of split that into several folds?
It's okay to split it into several folds. So ideally, it would be nice to use totally separate set. But again, if you don't want to lose your data, you have to do some kind of cross-validation. So yeah, you can set up your pipeline then and perform some kind of embedded cross-validations. So the internal layer is used to select all hyperparameters, and the external layer is used to estimate actual errors on kind of test set. So yeah.
Internal error validation is what you can report as.
Yeah, I believe that you can. So it's not totally independent because somehow you use all your data during the training, but in my opinion, it's a good way if you have very small samples.
And what do you mean by very small? In your mind?
Yeah.
Would that be okay?
Hundreds and even sometimes thousands of samples. It's pretty small. So
Imaging, we're never going to.
Yeah, I know. Yeah, for example, ImageNet is a famous data set for deep learning. It's 15 millions of images. Yeah, we don't have such data sets. Yeah, it's clear. So yeah, we have to perform some kind of cross-validation.
Do you have a favorite pipeline for neuroimaging? Like just off the top of your head, do you have something that you think works really well for trying to predict like neuroimaging features, metrics or something?
Actually, we don't work with functional MRI.
Not functional, just any.
We played a lot with structural connectomics, and we played with different approaches like somehow generate a vector of features, like calculate some graph metrics and for each graph, and then use this metrics as input. And then we can use kind of standard machine learning pipelines from scikit-learn, or we can somehow create a kernel based on these graphs, so somehow calculate distances between graphs. There are different ways to do this, and then we can estimate pi-RAS distances between all graphs in our sample, and then perform some kind of kernel method like SVM, kernel SVM with predefined kernel metrics, distance metrics. And another type of pipelines is deep learning pipelines for segmentation. And at the moment, I'm not really satisfied how do we usually perform cross-validation, because we do only a couple of repeats because it's computationally intensive. And but ideally, I'd like to do some kind of experiments to select different architecture or to play with different pre-processing methods, and then repeat, select someone to report, and then repeat at least 10 times, so 10 different cross-validations to be sure that the result is pretty reproducible. Yeah. Okay.